It's not the case that no cities are cities that experience an earthquake. And it's not the case that some cities are cities that experience an earthquake. So again, we're going to start off by drawing a premise diagram and a conclusion diagram. Premise diagram will have a label from our subject term, first word, or first letter of a significant word, and we'll have a letter for our predicate term, first letter of a significant word from that. So in my premise diagram, I chose C for cities from my subject term, and I chose E for earthquakes from my predicate term, and now I've got my premise diagram. My conclusion diagram, same labeling, subject on the left, predicate on the right, except that it's now labeled a conclusion. So now I'm going to use my premise diagram to graphically represent what would have to be the case in order for the whole premise to be true. Now this premise, like the first one, has an it's not that clause. And so again, we could figure out what would have to be the case in order for that whole premise to be true, or we can do it in a stepwise fashion. So we'll start off by looking at what it would take to make the embedded categorical statement. No cities are cities that experience an earthquake. What would we need to make that true? Once we know what that is, then we know our premise asserts that that statement is false, and so our premise diagram would have to have something in it that would guarantee that that true diagram can't happen. So we start off with our premise diagram, with our true diagram, and we say to ourselves, okay, this is a universal negative. I don't know if there are any C's, I don't know if there are any E's, but what I do know is nothing that is a C, nothing that's a city, is also a city that experienced an earthquake, is also an E. And so that area, that intersection between C and E, that would have to be empty for my standard form universal negative statement to be true, this embedded categorical statement. So I fill that in. Now I know what it would take to make the standard form statement true. My premise, however, denies the truth of that statement. It says that it's false. And so what we want to do to make our whole premise true in our premise diagram is to indicate graphically what would have to be the case if that universal negative statement was false. To make it false, we want to make sure that what makes it true can't happen. In this case, it's an intersection of C and E has to be empty. There can't be anything that's both because no cities are cities that experience an earthquake. So to make our premise true, all we have to do is make sure that this diagram can't happen. So if we put an X in that intersection there, then it will be impossible for that intersection to be empty. That means our universal negative is false, and that means our entire premise, a premise that asserts the universal negative is false, that will be true. Now let's go over to our conclusion. It's not the case that some cities are cities that experience an earthquake. Here we've got a particular affirmative categorical statement embedded in our conclusion. Our conclusion denies that that statement is true. So we'll start by looking at what it would take to make that categorical statement true, and then we'll look at what we need to make the conclusion true, given that it's denying that that standard form categorical statement is true. So this is a particular affirmative. Particular statements say there's at least one thing. It is a member of the subject class, and because this is an affirmative statement, it's also a member of the predicate class. So this is a statement that asserts there's at least one thing. It's C, and it's also E. So it's in both circles. It has to be in this intersection. So we put an X in. That's our one thing. Now we know, at minimum, there has to be at least one thing. Call it X. It's a C, and it's an E. That would make that embedded particular affirmative statement true. Our conclusion says it's false. So our conclusion diagram has to graphically depict what would have to be the case if that particular affirmative statement were false. To make it true, there has to be an X in that intersection, at least one thing in that intersection. So to make it false, there can't be anything in that intersection. And so we would shade that area so that now we've got a graphic representation of what would have to be the case if it's not the case that some cities are cities that experience an earthquake. Now we have our conclusion diagram. Here's what we need at minimum to make our conclusion true. We have our premise diagram. Here's how the world would be if our premise was true. If we make our premise true, that will mean there's an X in the intersection. That means that it will be impossible for our conclusion to be true. And so we know that making the premise true will not guarantee that the conclusion is true. And so that is an invalid argument in Boolean logic. If we get an invalid verdict for Boolean logic, we always have to test for Aristotelian validity. To test for Aristotelian validity, we don't have to worry about the conclusion diagram. It's fine the way it is. We only have to worry about our premise diagram, and we only have to worry about the subject class of that premise diagram. That's the only part of either diagram that changes as a result of the Aristotelian assumption are going to matter for. So we're going to look at our subject class of our premise diagram whenever we want to evaluate for Aristotelian validity. All the rest of our diagrams can stay exactly as they are. So our Aristotelian assumption says every class has at least one member. So the information that we get, the additional feature of the world that's added by that Aristotelian assumption in the case of our subject class is that our subject class has to have at least one member. So when we go to modify our diagram, again, we only look at the premise diagram, we only look at the subject class, and we ask ourselves, does that subject class have a member? In this case, our subject class has a member, so it satisfies that Aristotelian assumption already. So all the information that we get from the Aristotelian assumption is already in our diagram from our Boolean evaluation, and we don't have to change anything at all. As long as that subject class has a member, we leave it alone. We evaluate our argument again, this time for Aristotelian validity. In order for our conclusion to be true, there has to be nothing in the intersection between C and E. If our premise is true, there's at least one thing there. And so if our premise is true, it will prevent our conclusion from being true. And so the argument is again invalid, this time in Aristotelian logic. The last example I want to go through for direct inferences is this one. So in this one, we've got a premise that says no pomegranates are mammals. We've got a conclusion that says some pomegranates are not mammals. So we're going to start off again making premise and conclusion diagrams. Prominent word of the subject class, pomegranates, first letter P, left-hand circle. Prominent word of the predicate class, mammals, capital M, that'll be in our right-hand circle. Premise diagram labeled as premise, conclusion diagram labeled as conclusion. Now, we want to start with our premise diagram. Our premise diagram says no pomegranates are mammals. We're starting evaluating in Boolean logic under that Boolean interpretation. So we say, I don't know if they're P's, I don't know if there are any M's, but what I do know is that nothing that's in that P circle is also in the M circle. So for this premise to be true, it has to be the case that this area is empty. There may be other things that are true or false, but it has to be the case that this is empty. And so we would shade that area in. We always shade for universals. And so this is what has to be the case for that premise to be true. The intersection of P and M. That area where there's something that's both P and M, that has to be empty. There can't be anything like that. Then we go to our conclusion diagram. Our conclusion says some pomegranates are not mammals. It's a particular negative. Our particulars always tell us there's at least one thing, so they always introduce an X. There's at least one thing. It's in my subject class. It's in my P circle. It is not in my M circle. It is outside of the M circle. And so I put an X in P outside of M, like so. Now I look, here's what I need to make my conclusion true. I need at least one thing in P and only P. I look over at my premise diagram here. In that area, there isn't anything written there. That means that my premise doesn't commit me one way or the other. The world can be either way. And so there's nothing about making my premise true that guarantees that conclusion is true. And so that argument is invalid and Boolean. The next thing, of course, I'm going to want to do is evaluate the argument in Aristotelian logic. And just as before, I don't have to worry about my conclusion diagram. Changing that's not going to matter. I only have to worry about my premise diagram, and I only have to worry about the subject class, P. So I'm going to look at that P circle, the subject class of my premise diagram, and ask myself, does it satisfy the Aristotelian assumption? That Aristotelian assumption says that every class has at least one member. So I ask myself, does P have at least one member? Well, there's no X's at all in P. Can't be any X in here. And so the Aristotelian assumption tells me there is at least one member of P, and it would have to go here. So I put that X in, and I circle it to remind myself I'm only entitled to that bit of information only if the class P is in fact a good Aristotelian assumption, only if there are pomegranates. Otherwise, I'm not entitled to that information. That's how it got in my diagram. So now I look, in order to guarantee my conclusion is true, I need something, at least one thing. It's in P, it's outside of M. Under the Aristotelian assumption, I have something that's in P and outside of M if my premise is true. So now, before I write valid and Aristotelian, I want to double check and see, is this a good Aristotelian class? Is it a class that has at least one member? Is there at least one thing that corresponds to that subject term? So I look up there, pomegranates. Sure, there's at least one pomegranate out there. Therefore, it's a good Aristotelian class, and therefore the argument is valid in Aristotelian logic. Now, if instead of pomegranates, the subject class of this argument was, say, Pegasus, then that class is not a good Aristotelian class. It doesn't have at least one member. There are no Pegasi, and as a result, that argument would be said to commit the existential fallacy. Its logical structure is dependent upon the existence of members for each class, of at least one member for each class. But that class that I need a member for, it's not a good Aristotelian class. It doesn't have a member, and so it commits a fallacy of supposing existence, existential fallacy. In this case, however, there are pomegranates, and so the argument is valid in Aristotelian logic.